Geotechnics is essentially risk management. We live in a dynamic world. We have earthquakes, we have volcanoes, we have tsunamis, we have faults and faulting. These things get on the news. What doesn't get on the news is the fact that as your house or structure stands on its substrate, there are things going on. In the US, they say the damage caused by expansive soils outweighs, put together, the costs and the damage caused by all those others. Expansive soils take up moisture in the wet season, lose it in the dry season. Ongoing cyclical expansion and contraction of that clay will damage a structure. Expansive soils occur throughout the world. Then we have collapsing soils. Wind-blown loess that gets driven by, as I said, wind, that can also collapse. We have those in South Africa. Then we get consolidation taking place. You load a clay and initially the weight of the building is carried by the water and the pores of the clay, but ultimately that load will drive the water out, the clay consolidates, it settles, and your building is damaged. We have rock falls, we have landslides, we have, as I said, settlement of its different kinds, collapse. We have slope failures. We need to understand these things because essentially we live, as I said earlier, in a dynamic world. Planet Earth. It's made up of all sorts of geological materials. Those things are millions of years old. Africa, Europe, Spain, Italy. So it goes. We live in a dynamic world. Australia. Hello, Australia. India. Himalaya. We live in a dynamic world. So we cannot ignore these things on which we build our structures. So let's pay attention to them and let's do the work. So the person who manages that is the geotechnical engineer and the engineering geologist. So we need to go and spend time with this, understand what's going on, build a geological model, a geotechnical model of our site so that when the time comes, we can design things properly. We can design our foundations, we can manage the water, we can manage the hazards, we can manage the slope stability issues, we can look at how we're going to build retaining walls, all of those kind of things. So geotechnics, it's a vast topic. It really is a vast topic. I think people run away from it because a lot of people see it as a dark art. You know, when you're an engineer and you understand the properties of concrete or the properties of steel or the properties of the materials you're working with, it's very easy. You can go and look that stuff up on a table. And they can manufacture the materials so they comply to certain specifications. So you know pretty much spot on exactly what you're dealing with. But now soil and rock are two different beasts. And so it is a bit of a dark art. And you really have to keep your wits about you. You have to bring your experience and you have to go and get good data. Because geological materials by their nature are variable. Even across a single site, we can have clays at one end, we can have rock at the other. We can have alluvium where the river runs, and on the other side of the site, we can have deep clays, or again, we can have rock, whatever it happens to be. So we need to design our site investigation. Design our site investigation. What are we trying to do? What are we trying to do? What are we trying to do? To find out. But without getting too involved in that, let's just talk about the real issues. We need to know soil thicknesses. We need to know the soil types, because from that we can get an idea of their engineering properties. We need to know where the rock is. Where's the rock? Where's the rock? And by that I mean the rock level. How weathered is the rock? How weathered is the rock? Where do we put our foundations? Where do we take our foundations to? And then what are the engineering properties? Properties of the soil and rock. Of the soil. Of the materials. Let's say the materials. And finally, the groundwater. Where is the groundwater? Very important and often gets neglected. So I guess we must do this. Put question mark. How weathered is the rock? Where's the rock level? Soil types and soil thicknesses. So how do we go about finding that out? There are numerous ways. We can do a test pit investigation. So going back to our site here, we can dig a host of test pits across the site. If it's just a standard investigation and we don't know what to expect, we can just start digging. Maybe one here. Maybe pay some attention if we can get in one there. We can do test pits. Test pits are fantastic in the sense that they are cheap, they're quick, and they tell you a vast amount of information. They give access to the soil profile, we can sample it, and if need be, we can install a piezometer in the pit. And so they really are very useful in terms of getting quick, good, and valuable data. The next step up is to drill boreholes. If we're putting a multi-story structure and we need to know what's going on in the deep soil profiles, who knows? Sometimes this can be a bit arbitrary. Sometimes it can depend on how much money the client is willing to spend. But we do have standards to maintain, and that's often an issue in terms of trying to get a budget for a site investigation. How much money is the client willing to spend? They'll spend a fortune on the Italian tiles, they'll spend a fortune on the finishes, but they won't spend a little bit of money on trying to understand what the ground conditions are. And when the building cracks or it settles, the first things that get damaged are none other than those fancy finishes. Those Italian tiles aren't going to look so great when they're cracked. That fancy white facade isn't going to look so great when it cracks. So let's stop this thing settling. We need to understand. But to convey that to a client is our job. And sometimes, in fact, almost all the time we fail in that. And then we're fighting for budgets, trying to get the money to understand and do a decent job. And the client doesn't see value. It doesn't look fancy when it's below the ground. It seems like money's gone into maybe a black hole, maybe a deep dark one. Okay, so we need to find a decent budget and we need to keep some standards up. And we also got to look after the client to make sure he's happy, and we've got to reduce everybody's risk. It is all about risk management. So we're reducing the client's risk, but we also need to reduce our risk, because we cannot rely on our professional indemnity insurance to carry the shortfalls of a site investigation. I think one of these days we're going to have a massive failure and someone's going to go to court and they're going to get taken to the cleaners, and we're all going to catch a wake up because we cannot keep on as we have. I'm preaching a little bit here now because there's been a real serious neglect of site investigations and giving the professional guys, the geotechnical guys, a decent budget to do a decent job. Okay, so I'm over that now. You might hear a few more of these tirades as this series continues, but I thought I'd just get that off my chest now. So we're trying to manage everybody's risk, trying to manage our risk, we're trying to manage the client's risk. No ways would I ever put up any structure knowing what I know about geotechnics without understanding what the ground conditions are like. I would not even dream of it. You know, we've seen in this, I've seen, and all the other people who worked in this profession have seen all sorts of things going on over the years, and you come and you say, no guys, you can't do this. Are you mad? Have you not done a little bit of work? Or you get asked to come and solve a problem after the event. Hey guys, my house is settling. I've got cracking. Oh, we need some underpinning. Ah, my building's falling over. My retaining wall is not doing what it's meant to be doing. Well, you come there and you kind of shake your head. Yeah, well, like you think, you know, it serves you right. If you just come and spent a little bit of money, it could have saved you millions, literally millions at times, in the future. But now you're sitting there, we're trying to underpin a house. Yeah, we can do it, and it's sort of successful, and you've got to bring the guy in, and it's 10,000 Rand a pile, and you've got to put 20 of these things along the perimeter of the house, and you're still not sure if it's going to work, and you might have to go inside the house and drill through the concrete slabs and underpin. Guys, first of all, your house is going to be full of dust. It's going to be disruptive. And then at 10,000 a pile, and you've got to put 10 of these things, and you're in for 100,000 bucks. You could have got the geotech done for 20 or 30,000, 10,000, who knows? Someone just to come in and put it in, a little bit of professional input, so that everybody sleeps well at night, including the homeowner, the building owner, the developer, because we need to do this stuff. We take insurances out, but no one talks about those insurances in terms of understanding the founding conditions which we're putting our structures up. So, okay, I do think I'm going to stop there now. So a test pit. So we dig a test pit, and we've got colluvium, and we've got residual soils. Residual. And then we get another layer of residual, and then we get this is the bedrock, the highly weathered shale, or whatever it happens to be, and colluvium. Hey, the water might be sitting somewhere here at the interface. I'm just speculating here. Yeah, we understand where the water is. We dig a pit, there's refusal. We know that there's a decent founding horizon down here. That's ground level, of course. We're standing here. I don't know if this is, we've got to not be sexist about this. Might get into trouble. With the TLB, we can take samples of the different soil horizons as we go down, put that in the laboratory for testing, which goes back to what are the engineering properties of the materials. So those samples, S, it's just right, S here and S. We know where the water is. We can take our foundations down to this material or this material, depending on how stiff it is, how we think it's going to behave. Soil thicknesses, so we can measure that. Well, that's 0.3 for the colluvium, and that's let's say it's 1.3, 1.8, 2.1 is refusal. Now we understand. We're starting to get a picture of what's going on. We dig test pits across the site. We find the rock is closer to the surface here. We find it gets down into deep, wet alluvium down there. We start building a geotechnical model. We understand what's going on. If we have to drill a borehole, let's come over here. We drill a borehole. Here's the ground surface. Down it goes. I'm not going to try and draw a parallel one here. That's the ground. Here's our engineering geologist. She has to come and log this hole. Tell the driller what to do. Drills down. But hey, down we go. We're drilling down on the colluvium. We're finding that the water table's sitting at 33 meters. We've got soft mush all the way down. It starts to stiffen up. Hey, we drill down into rock down at 35 meters. Fantastic. So we get drill cores here. We log that. We log the soil profile. We start to understand what's going on. We put several of those boreholes there. We do standard penetration tests. We get the N values, every 1.5 meters. The issues around that test too, but this isn't the place to talk about that. So we get a profile of the soil profile in terms of its N value, which we can put into the bearing capacity equation. And hey, we're building our geological model. If we need to understand the slope stability, we need to cut undisturbed samples from the test pits. Maybe we get them out of the boreholes. We go to the laboratory, we do triaxial testing. Sigma 1. There goes Dino, he's fallen down. Sigma 1, Sigma 3. Doing it sideways, Sigma 3, Sigma 3. We load it, 3 different, and we plot ourselves more circles for the undrained. Tau equals C plus sigma tan phi. Shear strength parameters. Cohesion and the friction angle, and of course sigma is the load. Sigma 3, sigma 1, sigma 3, sigma 1, sigma 3, sigma 1. That's undrained. Drained. If we do those tests, sigma 3, sigma 1. So there's the undrained version, which is reflective of the immediate conditions, saturated after excavation takes place, or the drained version where the slope has had time to drain, and then we get a different scenario playing out. So we understand what's going on, we take our samples, we test them, slope stability, we can use C and phi, which I spoke about earlier. We use C and phi in our analysis of the stability of the slope. So that's a triaxial test. Okay, so this, let's just write it here. We're getting a lot of information coming at you. Triaxial test. The cheap version, not anywhere near as good, because unfortunately you're shearing a sample through a known line, but if you shear this way and that way, then you also can come up with your shear strength parameters, tau equals C plus sigma tan phi. A wonderful thing. But if we don't do the laboratory testing, we're guessing. We can look up in the book. What are the typical shear strength parameters of a soil, of this and that? And we look it up and then we're guessing. Yeah, well, we can run all these different analyses in the software, but what is the number? What is the number? We guessed it. Now, am I going to stand up in the court when the judge says, Mr. Davie, you were the geotechnical professional on this job. The slope has fallen down. It's enveloped a whole housing estate. There are 2 people dead. Everybody's cars are now under mud. The houses are damaged. You for the high jump for whatever that figure is. 20, 30 million, 10 million? I don't know what compensation we have to pay out. Now, am I going to tell the judge, well, look, I didn't push to actually do any laboratory testing on the samples that I took out of the slope? No, I looked my stuff up in a book. Well, what book was that? Well, it was this book. Oh, but didn't you feel led to be responsible and actually do the testing as per the dictates of your profession? Yes, Your Honor. I did think that, but I tried to get the client to pay and he didn't want to, and blah, blah, blah. You are on a hiding to nothing. So let's pay attention to these things. Preaching again, sorry. We are managing risk. So if I'm doing a slope stability analysis, I want to know what my C is. I want to know what my phi is. Yes, I might go back and look at the literature to compare what our results are like in relation to similar soils, which there's been a huge body of work done over the last 50 years. And I will look at those things because it would also be negligent of me not to do so. We have to look at typical values and say, well, look, my results and these results, yeah, okay, they look pretty similar. If they don't, what is going on? So let's go and do some work. Let's go and do site investigations. Let's characterize the site. Let's get the soil thicknesses, the soil types. Find out where the rock level is, how weathered is the rock, and where do we take our foundations to? What are the engineering properties of the material, and where's the groundwater? So now we're starting to answer some of these questions. We drill boreholes. We know where the groundwater is. I was meant to draw that there. In our test pits, for instance, on a shallow investigation, we know where our water is. We can understand. The water is very important. No one pays attention to this. We could actually just stick a piezo in here. It's not the best way of doing it. And backfill the hole. At least at some stage you can come and put a dip meter. Very hard to draw 2 parallel lines, especially when you're not. Put a dip meter down and we can measure where the water is. Water is incredibly important in terms of designing foundation design. And it affects your shear strength, it affects the in situ weight of the soil. There's a buoyant effect of the water trying to lift up the in situ materials. It affects your consolidation, it affects your heave. So we need to pay attention to these things. So I think I've given us a broad overview why we need site investigations. I've talked about structures on the surface. Often we have tunnels. We're doing site investigations for tunnels. We need to drill some holes. There, we're still managing risk. I won't rub that out. We got a long tunnel. There's an open hole in the ground. We might have to open it up and support it. Rock bolts. The question is, what's the condition of the rock mass? Is it very fractured? Is it a nice, beautiful white granite? I worked in a tunnel in Italy, beautiful white, hard granite. An absolute dream to tunnel in. It's a nice little story, this. It was in the Val Brembana, north of Milan. They were putting a bypass through the town of San Pellegrino. San Pellegrino, where the bottled water comes from. Delicious water, eh? I would recommend it to you, and I get no commission for saying that. There's a fault, granite here, granite, and this Riva di Salto formation. Riva di or Riva da, I think di Salto. They're driving a tunnel this way. This was awful, squeezing black shales. I remember bringing some samples home to test. It was on my master's project. The stuff was like polished glass. The discontinuities were smooth, as smooth as this board, and black, polished. It was like obsidian that had been saw cut. Beautiful, beautiful, beautiful surfaces. Shear strengths of, 12 degrees, fire. Maybe if we were lucky. Maybe even lower. Awful. And then we crossed this fault. They built a bridge here. There was a stream that exploited this fault, and they built a bridge, and the tunnel boring machine came out here, crossed the bridge, and went into this beautiful white granite. An absolute dream to log. But they had drilled boreholes all along this tunnel. So when they got here, they had some idea of what to expect. Of course, there's also the geological maps to be consulted and all that historical work that can tell you so much, even before you start thinking about drilling boreholes and doing that kind of work. You go back to the databases that are available to you. So to understand what's going on this side of the tunnel, it was full of, well, it was actually a circular. It was a TBM board, tunnel boring machine board, pilot tunnel, and there were just these beautiful round steel sets that they had to put in, bolted together to support. It was just a rib of the inside of the whale. You just go down its entire length. Where on this side, they just drilled it and it stood up by itself. They did nothing. They literally did nothing. There was no rock bolts, there was no support. It just went straight across that bridge and into this beautiful, beautiful. They had to support the portal here. Obviously there's colluvium and soft ground. But once they were in, it was a breeze. So we need to understand what's going on. We do need to understand. So we drill some boreholes, we do some mapping, we do a whole lot of work. Tunnels here in South Africa, Hex, back in the 1980s. I went to a talk at SIAG earlier on in the year, January I think it was. Amazing stories. I think that thing was budgeted for 28 million or 30 million rand back in the day, and it went over 300 million, which is phenomenal. Court cases, the lawyers made a lot of money, some guys lost a lot. Because people needed to pay attention to the rock mass. What's going on? Rock masses. Sorry, I should change my color. Rock mass. We've got all sorts of things going on here. Joints. You take that support out, those pieces are going to fall out. Bang, bang, bang. On this side, they're not really daylighting, so it's probably safer here. So we can draw a smiley face there. But on this side, no. We're going to have sad faces, and here it's going to be sad faces because there's work that has to be done. The only way to support that, we need to know before we get in there what it's going to cost to do it. What are we going to do? Are we going to need steel sets? Are we going to need steel sets? We need to budget. Are we going to rock bolt it? We need to understand what that's going to cost. We don't want to arrive there and say, oh, my goodness me, look, it's far worse than what we thought. We spent a little bit of money at the outset. We understand what we're facing. We can price it. We go there forewarned as forearmed. So we can go in there and do the work without getting huge surprises. Oh, what? No, we got to find this money. So the geotech guy is the one. She's the one who's going to save your backside. So let's look after the geotechnical people. We're going to manage our risk. Have I really been holding forth for 32 minutes? We're going to have to manage our risk. Site investigations, tunnels, bridges, pipelines, all of these things. So we need to understand and build our geotechnical model, which we can then just pass on to the engineer, and then he or she can do her design. But let it be said, I think, and I truly believe this, an engineering geologist needs to do this work. Engineering geologists go to university. They start out first year, second year, third year, and maybe a fourth year honors. It's rock identification, it's mineral identification, it's geochemistry, it's igneous petrology, it's metamorphic petrology, it's sedimentology, it's paleontology, it's structures, and not structures in terms of engineering structures, but structures in terms of folding and faulting and how the rock mass behaves, which are directly applicable to an engineering point of view. So geologists have an understanding of how the earth works. I remember doing a job in Durban along the Umlaas River many years ago. 6 weeks of test pitting. We don't get those kind of jobs anymore. So I don't know what's happened there either. I dug test pits. I was thin as a rake, fit as a fiddle, and we dug test pits day after day after day. And then we were in all these sediments, residual sediments, and colluvium and alluvium stuff along the Umlaas River. And I was finding all these boulders where I didn't think there should have been boulders. And I'm thinking, what is going on here? And then it dawned on me that I was actually digging in old alluvial terraces, where the Umlaas River was flowing at a higher level, and those terraces were now left up above the river, and we were digging up all these big rounded Natal group sandstone boulders. Now an engineer wouldn't have understood what was going on there. And that was just one small example. So geologists go there, they understand how the world works. They've been trained, they've been chased up and down the hills by their professors to look at rocks, to open their eyes, to understand, look, and draw conclusions. It is an observational science. They've got to look and gather data. So those are the people, boys and girls alike, who need to go out in the field and get the data because they're trained to do so. I say this with all due respect to the geotechnical engineers and the engineers themselves. There's such a crossover between the engineering geologists and the geotechnical engineers in terms of what they do. But one is coming from a slightly different point of view compared to the other. And yes, there's all this common ground that we need to meet on and not fight over. It's not no man's land. It's not full of barbed wire and shower holes and no dead bodies. It's common ground. So let's go and discuss how we're going to find each other in that space. So geologists, go out and do your work. If you're an engineering geologist, you need to get up to speed in terms of what you need to know, that the engineer needs to know. So please understand that there are foundations to be constructed, there's bridges to be built, there's tunnels that need to be bored, there's groundwater and all that engineering work that needs to be understood, so you are responsible for the geotechnical model. So pay attention and go and learn some engineering. And vice versa for the geotechnical engineer and the engineers. Guys, you need to understand a little bit about the geology so that those minds can mesh and we find that commonality. And that's not turning into a bloodbath on no man's land as the bullets fly and the big field guns lob shells over our heads. I hope I've kind of emphasized the importance of geotechnics and why it's important, how it assists us in managing risk, and how we need to go about getting that information so that we can make the right call and understand what we're doing. And so when it comes to actually designing the foundations, building the retaining walls, we're armed with good knowledge, and at the end of it, we all go home and we all sleep well, and we don't land up having friendly discussions with the judge and the court. So thank you for your time. Please subscribe to the link below. We're trying to build a channel, we're trying to build a geotechnical community, we're trying to raise the standards, and we're trying to have some fun. So yeah, please subscribe. You know what to do. We've done this all before. If you like what you've seen, click a like, please visit us at the website geozone.co.za. We try and blog, we try and put stuff up there, and it's all great fun. It's all a great way of keeping everybody hooked up and everybody linked and everybody entertained, and it raises the standards. As some old driller used to say to me when I was a youngster working for a site investigation company in England, he said, at the end of every job, I'll see you in some corner of a field somewhere. I look forward to it.